You know when you're hot and you know when you're cold. So you probably know at least something about heat transfer. So let's go ahead and get started to improve your problem solving skills in thermodynamics related to heat transfer. We're going to talk about heat transfer and heat transfer rate. So first, let's apply some common sense 101 and test your ability to identify heat transfer. Okay. Gee whiz. So here's a nice Pyrex bowl. It's got water on it sitting on a stove. It looks like either a propane stove or a natural gas stove. We've lit it off and there's a hot flame. And so, you know good and well, your common sense tells you that heat is being transferred into the water from the hot propane or natural gas exhaust. So you see that I've shown, just for clarity, so what if I had a thermo problem and I needed to identify a closed system? You can see that I've shown in the a general idea with that dashed line of where the closed system would be. But by golly, you've got a good physical feel for the heat transfer involved if this was one of a thermo problem. Okay, another common sense 101 idea. You've got a toaster oven, and you're trying to make your delicious pizza in the toaster oven, and you know good and well the quartz electric resistance rods down low and perhaps even above higher on the broiler side of your toaster oven, they're on and they're heated up to red hot, as you can see. And so, of course, the conclusion is heat is being transferred into the toaster oven space, probably being both the pizza and the air inside your toaster oven from the hot quartz electric resistance rod. There's a heat transfer problem, isn't it? You got that nailed. So here's another one. Common sense. So this is in the manufacturing process. We've got a steel rod that's being manufactured. It's just coming out of a hot furnace, maybe tempering or something like that. And you can see with your eyes, it's nearly red hot. And so your common sense tells you, you know good and well that heat is being transferred from the steel rod into the surroundings. And then over here, here's a steel part that can be handled with tongs or something. And so heat is being transferred from the hot steel part into this oil cooling bath for some reason. But you know that it's a heat transfer situation, isn't it? And you know where the heat is being transferred from and to. So let's figure out so back to thermo problems and the good old example, tried and true piston and cylinder. Let's say you've got a problem associated with a piston, the closed system contained within the piston and cylinder, I've shown with the dashed line, and you want to depict heat flow into that closed system. So I've shown it as a big fat arrow, labeled it QN. And notice how that arrow is passing across the system boundary. It's not just sort of pointing into it, it's crossing the system boundary. And so similarly, from previous work, I'm showing that the closed system is doing work, and I'm showing a big fat W out, work out arrow, and it's crossing the system boundary. So, but on the heat transfer, remember that heat can flow into a closed system or it can flow out of a closed system, and it applies same thing to open systems as well. Let's see. Key point on heat transfer. I think I just made it. Heat transfer is a means for transferring energy across a system boundary, and you see how that's similar to work. And so it's just a reminder that when you draw your sketches, show these big fat arrows crossing the system boundary, not just sort of pointing into it. Both work and heat are boundary phenomena. More key points about heat transfer. How can you figure out when something is heat transfer and something is work? Well, let's see. I remember work. Work can be considered lifting a weight. That doesn't smell like heat transfer at all, does it? But one thing you do know that heat on its own only flows from a higher temperature to a lower temperature, and that is a key for identifying heat transfer. You've got you've got two maybe substances or two systems, and one system has got to be hotter than the other. That's the only way you can have heat transfer. And so in my little sketch, you can see, just try to drive it home. I've got in the surroundings here, my surroundings are hotter or warmer than what's inside the system, and the system is either cooler or colder than the surroundings. So that's the point I'm trying to make there. Let's see what else I got. Oh yeah. Heat transfer is identified as a result of two systems being in thermal communication with each other, and what I previously said, one system being hotter than the other. So there's two requirements for heat transfer: is one system's hotter than the other, and the other is both of those systems are in thermal communication. So what does that mean in the real world? In our example, it means that the cylinder wall must be made of some type of conductive material. So if you think back about some previous videos, remember I showed a picture of a thermos jug, right? Where the jug, there's two vessels, and in between the vessels, there's an absolute vacuum. Well, that means that the surroundings and what's inside the thermos bottle are not in thermal communication because there's no mass in between them. So anyway, important point is the cylinder wall is made of some type of conductive material. And we're going to have some thermo problems where we come in and say, we have fully insulated the wall of that cylinder. We have fully insulated with a big bunch of thermal insulation, styrofoam, a thickness of styrofoam. That'll be an engineering method by which we prevent thermal communication. So I hope you get the idea. So as drawn, this piston and cylinder wall is made up of some conductive material, and we've got heat flowing from the surroundings into the system. Okay, a way to maintain your sanity. This is Jay's recommendation for maintaining your sanity in this class. One of the many things. When I always write Q sub n. Don't just write Q. In your textbook, I believe they just write Q for the textbook. Train yourself to always write Q sub n, just like I've shown on the sketch. Now, when Q sub n is a positive number, that means that heat is transferred into the system. Qn, positive number, into the system. In my sketches, I always show the arrow flowing into the system, but my number may result in Qn being less than 0. Well, that's the signal that heat's rejected from the system. But I don't go back and change my sketch and flip my arrow around. So this is the way I maintain my sanity when working on homework problems. You are going to want to figure out your own method for doing it, but this is the way I keep myself straight. And my professors harped on this, right? So I didn't invent this idea myself. My professors harped on this, and one reason was because I was always getting tripped up by either switching my arrow or something like that, or trying to be to outsmart myself, and I ended up outsmarting myself. So I strongly recommend that you develop a habit of writing Q sub n and then numerically evaluate the values to see if it's a positive or negative number. Your common sense is going to help you expect, will the result be positive or negative? What if the surroundings are colder than the system? Well, you're going to get a Qn less than 0. Your common sense, if this is hot and this is cold, you darn well know that heat is rejected from the system as long as this is a metal or a conductive cylinder wall. Okay, so the other thing is I strongly recommend that you do never write Q out. Strong recommendation for it. Some instructors do that, but at least for maintaining your own sanity, for maintaining my sanity, I never write Q out. All units on this page relate to heat transfer. So let's look at units. Over here on SI, the easiest part, joules represent measures of heat transfer. Well, that's a Newton meter, so that could work too. A Newton meter can work, but a joule is a measure of heat transfer. Similarly, a kilojoule, just multiply a joule by 1,000. Kilojoule is a very common way to express heat transfer. Over here on the English side, the traditionally accepted way to express heat transfer is in BTUs, British thermal units. And we'll explain what a BTU is a little further down the road. But for right now, if you've gotten into your conversion factors page, you have discovered that there is a conversion factor to go from BTUs to foot-pounds force. And so when you're working through engineering problems, certainly a valid unit for heat transfer is foot-pounds force. But in terms of final answers, we're going to be looking for BTUs in terms of units for heat transfer. Now we're going to move on to heat transfer rate. What's heat transfer rate? And so my little example problem here is something you're quite familiar with. So here's a pot of water sitting on the stove. The propane or natural gas is burning there, exhaust gas, and heat is being transferred into the pot of boiling water, isn't it? And it's doing it, and you're doing that for a long time. It takes a long time to boil water, especially if you watch it. It seems like it takes longer to boil when you watch it than when you don't watch it. But anyway, want to talk about the rate at which heat is added. So this is very commonly observed, right? So you're adding heat at a certain rate for a certain time. And so this is good old common sense, is the amount of heat added to this pot is going to be the rate at which we're adding heat times the time. Simple as that. It's not even like a differential equation for this one, right? However, do recognize the way we're going to depict the rate of heat transfer in this thermodynamics class. It's not QN, it is Q dot. We put a dot over top of the QN, and that signifies to all other engineers, not just your grader, not just your instructor. Q dot N, all engineers recognize that as the rate at which heat is transferred. And they'd be okay, so Q dot N, that's the way we depict the rate of heat transfer, not just how much heat is transferred. So here's an example problem. Common example problem. Heat is added to a pot of water at a steady rate of 1,500 watts. I picked 1,500 watts for a reason. So if this were an electric hot plate instead of a gas stove, typically a hot plate's going to be rated at about 1,500 watts, kind of like a hair dryer. So heat is added to a pot of water at a steady rate of 1,500 watts for 10 minutes. You got it. Okay, heat the water, sit there for 10 minutes, pull it off. And I want to say, how much heat was added over that time period? Well, let's do the math. So QN, so here's our fundamental. QN is equal to Q dot N times time, as long as we're adding at a steady rate. Oh yeah, there it is, steady rate. So that's going to be a constant number. Time, 10 minutes. All right, let's do the math. 1,500 watts times 10 minutes. That's 15,000 watt minutes. That's not going to work for us. A watt minute, nobody really knows what a watt minute is, but by golly, we know what we need to express our answer in kilojoules. So let's figure out, how do we do that? We'll write down 15,000 watts, that's a joule per second, times a minute. Oh, now we've got joule minutes per second. That's not much improvement. So we study this, we say, I need to get seconds, I need to get these times, these time frames to cancel out. I do remember that there's 60 seconds in a minute. I multiply by unity, and now I can visually cancel my units. I've got minutes in the numerator, minutes denominator, they cancel. Seconds numerator, seconds denominator, they cancel. And so I'm going to do the math to get 900,000 joules. And right, that's a lot of zeros. So as an engineer, I'm going to slip that decimal 3 places to say I've got 900 kilojoules of heat 900 kilojoules of heat was added to the pot of water over the 10-minute time period. Simple as that. But you do see that this, you would not get full credit. If this were this would be a simple homework problem. If you were to express it, Qn is 15,000 watt minutes, you would not get full credit for that, at least not in my class. So let's just look then at the typical units of heat transfer rate. So remember, put a dot over top of Qn, for that's the rate at which heat is transferred. Okay, so over here, it makes sense, joules per second. Joules per second is a rate, or energy rate. Well, what's a joule per second? That's a watt. So watt is a very preferred. Watts, kilowatts, or megawatts are the preferred units to express heat transfer rate in SI. How about over here in English? Same idea. It's going to be BTUs, British thermal units, per time. It depends on the nature of the problem. BTUs per hour, or BTUs per minute, or BTUs per second, any of those are going to work. So those are the units of heat transfer rate. So notice the time component over here. Over here, the time component is kind of hidden, isn't it? A watt. So a good engineer knows that a watt is a joule per second. And that's how you know there's a time component in watts. Well, that brings us up to the recap pretty quickly. So what is our recap? Heat transfer is a means for transferring energy across a system boundary. And so I want to make the point here is that heat transfer, similar to work, is a boundary phenomenon. Okay? So a system does not possess heat, and a system does not possess work. So be sure to recognize that. Both heat transfer and work are energy transfer phenomena that occur across a system boundary. That's really, really important for mastering thermodynamics. All right, next thing. Heat on its own only flows from hot to cold. That's common sense 101. So some folks might not want to believe it, but it's true. I've never observed heat flowing from cold to hot on its own. There's some subtle things in that statement, and you're going to get to be really good at that a little later on, and we're going to save that for a little later. Heat transfer is identified as a result of two systems being in thermal communication with each other and one system being hotter than the other. So that thermal communication thing is critical, and that's right out of your textbook. So strong recommendation to at least browse the material in your textbook. And then remember that my suggestion to keep yourself sane is don't just write down Q. Write down Q sub n, and then let the numerics of the problem guide you in terms of understanding, is Qn a positive number? Heat is added to the system. If Qn is a negative number, heat is rejected from the system. So that I now declare you almost an expert in knowing how to deal with heat transfer, but you're going to need, there's another very important fundamental coming up for you to be able to quantify heat transfer for certain engineering situations. And so next up, I'm going to talk a little bit about transferring forms of energy from one form into another form. And you're getting perilously close to becoming really a good practicing young engineer once you get a better feel for how these forms of energy can be transformed from one into another. Hope to see you then.